Welcome, this is Mr. Hyatt, and I'm going to talk quickly about gas stoichiometry. What's great about this is we're not learning anything new, we're just combining two skills that we already have. So, first and foremost, we need to know that we're operating at STP. We talked about STP last time, I think, but standard temperature and pressure means pressure of 1 atmosphere and a temperature of 298 Kelvin. So that will be part of our given on both of the sample problems, and then you'll see on your practice problems as well. So basically our problem solving strategy is going to be really similar to what we've done in gas laws and stoichiometry because we're going to be combining those two skills. So we'll still list our given and need. We'll identify which gas law needs to be used. That should be really familiar from the last few days. And then once we apply our gas law, once we apply our gas law, most times we'll have to do some sort of a conversion after we get our answer. So it's really important that you focus on your need and you figure out how to get from A to Z. Like I said on 4, our need may be, we may have to use stoichiometry to get from, say, moles. If we do an ideal gas law and we solve for moles, we might need to go to moles of another reactant or a product or something along those lines. Or we might need to do a stoichiometric conversion and then plug it back into another gas law. And I've got an example of that here in just a minute. So let's just dive into a sample problem. So you've got one listed here. Calcium carbonate decomposes. That just means it breaks down at high temperatures to form CO2 and calcium oxide. And you see the equation written there. It's balanced, so we can dive in. How many grams of calcium carbonate will I need to form 3.45 liters of carbon dioxide? Problem solving strategy number 1 was list my given and need. I've got that done on the screen for you. I just pulled the 3.5 liters of carbon dioxide from the text of the problem. The temperature and the pressure came from that first slide. Remember that we're at STP. So since I have a V, a T, a P, and I need a G, I don't have any gas laws that have mass, but I do have gas laws that have moles, and I remember how to go from moles to grams. So if there's one that has P, V, T, and N, that might be a good start. And that to me sounds like an ideal gas law equation. We know we always have our R value that we can look up on our reference sheet. So here is the kind of stepped out ideal gas law calculation. I plugged in my P, my V, my R, and my T. Then I simplified there, did my multiplication. I did my multiplication here. That allowed some of my units to cancel. And that got me to 0.1411 moles of carbon dioxide. But I don't need moles of carbon dioxide. I'm going to moles of carbon dioxide so that I can get to grams of calcium carbonate. That's something I didn't mention earlier. I've got different species here. So I'm going to have to figure out how to get to moles of this thing. Once I get to moles of this thing, I can do a lot with it. Just like we did with molarity, all the stuff in the last unit, it's all about getting to moles. That's why I call the mole the heart of chemistry. So since I'm not all the way there yet, I'm going to need to do some stoich. I've got moles of CO2. I can use a mole-mole ratio to get to moles of calcium carbonate, and then I can use my molar mass to get to my final answer, which is 14.12 grams of calcium carbonate. So I followed my problem solving strategy. I was able to work through the gas law calculations, but that didn't get me all the way there. A lot of times these gas law calculations are just to get us to moles, and then we'll use stoich to get somewhere else. Sample problem 2. Ethylene burns in oxygen to form CO2 and water vapor. There's an extra step in this one. This is going to be, we're going to need to use a gas law twice here. So how many liters of water can be formed if 1.25 liters of ethylene are consumed in the reaction? Consumed means used up. So again, listed my volume from the equation. My standard temperature and pressure are there, and I need liters of water. Again, different species in my given and need. So sounds like ideal gas law to me again. Work that calculation here. Units are canceling. I've got a unit issue here. That should be mole Kelvin. So then, go through the math. I get 0.051 moles C2H4. But again, that's not what I'm looking for. I don't need moles C2H4. I need liters H2O. So I'm going to have to do some stoich. I don't know how to go from moles of one thing to liters of another. But I do know how to go from moles of one thing to moles of another. So at least now I'm in moles. I'm in the right species. I've started with the information that I've been given, and I've worked forward to where at least now I've got some information about water. At this point, I'm kind of stuck. What do I know to go from mass to volume? Well, if I had molarity, I could do that conversion real easily. If I had density even, I could probably do that conversion, but I don't have either of those values. So I'm left with trying to piece together the information I have to try to figure out what could this volume be. Well, if I now plug this in as my N in an ideal gas calculation and solve for V, that's how I can figure out my volume. So here's that worked out. Same pressure as before because we're at standard pressure and we're at standard temperature. I got that same unit issue. Standard temperature and pressure, my R value is what it always is. And I just plugged in my N value that I solved on the last slide. So I got this 0.102 moles of water, plugged it in, worked it out, gives me 24.45 liters of water. So work through the practice problems. Take your time, work slowly, write big, give yourself space. And I really expect us to do really well. If you have questions, don't panic. Shoot me messages through Canvas. Bring them to me before school. Come see me in homeroom. We'll get it figured out some way.